All right. Before actually we move forward, I wanted to show you what is done in your NCERT textbook. So, this is what is the working of a transistor as an amplifier, which we have already discussed, if you remember. So, this is the total input voltage, whatever we discussed, and the total input voltage is dropped partially across this resistor and partially across this base emitter PN junction. So, potential drop across the base emitter PN junction and plus the voltage across this external resistor is the total input voltage. So this total input is equal to this voltage plus this voltage. You can see it here also that the total input voltage here is equal to the potential difference between this and this and potential difference between this and this. The potential difference between this and this can be written as IB into RI, and potential difference across this can be written as IB into RB. This is the input resistance. Anyway, this makes much more sense when we write the change, because we know the concept of the dynamic resistance in case of diodes, which relates the change in input voltage, the change in base emitter voltage with the input resistance. Anyway, so yeah, so here it is, your NCERT textbook. I hope you can see it. Here also, if I zoom in like this, a little bit less. Okay. So this is what is written here, whatever we have written, this VBB. See, they are not applied any, in this case, actually it's making the remaining thing dark actually. Now, so here in this case, they have not applied anything here. This is simply VBB, and this VBB is equal to VBE plus IBRB, which is the normal Kirchhoff's law for the input circuit. Now what they have done is, to this VBB they have added this VI. Well, like when VI is not zero, that means the fluctuations are not zero, there are some fluctuations, so the total input voltage becomes this DC biasing voltage plus this VI. Unfortunately, what they have done here in this NCERT textbook page number 498 is that they have done a typing mistake which have not been rectified surprisingly within so many years have passed. So what is the typing mistake is, see, instead of this VBB they have typed here VBE. So actually this should be VBB plus VI, which is the total input voltage. So total input voltage, that was VBB, initially was VBE plus IVRB. Now because of the addition of VI to the input voltage VBB, so the total input voltage becomes VBB plus VI. So when the voltage was only VBB, that VBB was dropped across VBE and IVRB, and now when VBB is increased to VBB plus VI, so this becomes VBB plus IVRB plus this. So this VI becomes this one. So VI is equal to delta IB RB plus RI, and that is exactly what we have also written. If you remember, that's the same equation. This one is written where it is here. You see, this equation and this equation are same, or this VI is equal to delta IB into RI plus RB, and this VI is equal to delta IB into RB plus RI, this same equation, and we have also written it here, this one. So that is what I wanted to show you, and whatever expressions we have got finally for the current gain and voltage gain, the same expressions are being found here. So this is minus beta RC by R VI, and this is minus beta RC. See, instead of RC they have written RL, which is the load resistance, and it doesn't matter whether we use RC or RL, as we have already discussed it. So that is what is the voltage gain, AV, minus beta RC by R, and this is minus beta RL by R. So I hope this transistor as an amplifier is done. So let's just remove this part now. Okay, what is this? So moving ahead now, what I have here is this transistor circuit. Where is that transistor circuit from? Here it is. This is a typical NPN transistor in a proper active state. So this is a NPN transistor, as you can see from this arrow, NPN, and this is the emitter. Now now obviously this p side base and n side emitter, so this should be connected, this p side base should be connected to the positive terminal, n side should be connected to the n side emitter, the negatively charged negative terminal here. Similarly, this n side should be connected to the higher potential because of reverse biasing. So this is a typical circuit of NPN transistor in case of active state. And now there is another way of drawing this entire circuit, which is when we earth this. See, whenever we earth just one part of the circuit, nothing happens. It's just that the potential of this becomes 0. Now if this potential becomes 0 and this is all connecting wire, this potential is 0, and so as we go from here to here, we get a potential of plus VBV, isn't it? Similarly, when this is 0, this is also 0 volt, this is also 0 volt, and as we go across the battery, we get an increase in potential, and we start from 0 and we go to this VCC, the positive high voltage. Okay, so we can make any part of the circuit having a, see, we can make a potential of any point 0, doesn't matter, all the potentials will be automatically adjusted. For example, if we make this potential of the emitter instead of 0, let's say if we make it x volt, so if we make this entire thing x volt, then this becomes x volt, and as we go from here to here, we get an increase in potential of VB. So whatever potential we started with x volt, after going here, we get x plus VB. So if this x here, then it is this point is x plus VB, and if it is 0 here, this is simply 0 plus VB, basically, which is VB only. So nothing significant happens when we connect just one part to earth. Earthing just means taking that voltage as a reference. It doesn't necessarily actually mean that we are connecting it to earth or ground or something. It's just that you will learn about it in more detail when you actually make these circuits using transistors, resistors, and batteries in a breadboard. So just a reference potential. Now, so this is 0 volt, which is earth or the reference potential, and with respect to this we apply this VCC. So what is generally drawn here is, instead of drawing this entire loss, what we just draw is this VB and this VCC. What it means is, let's say when we draw this transistor here, and there is the transistor, then there is this RB, and there is this RC here. We know that this emitter is at 0 voltage, isn't it? So instead of drawing this battery like this, what we say is, because we know that this is 0 volt, then this is VCC, then we say that this is just a VCC, just like that, plus VCC. That's it, which automatically means that there is a battery from this VCC to the earthing, which is not drawn, but this VCC plus VCC signifies the battery. Similarly, instead of drawing a battery here like this between this earthing and this, and thereby supplying a plus VB value of potential here with the help of this battery, what is written simply here is this VB plus VBB, which means when automatically when we can come to understand that there is a VBB which is written over here, we can automatically understand the how do we supply this positive potential, or with respect to what there is a potential, positive potential. With respect to this 0 volt, there is a positive potential, which means with respect to this 0, there is a positive potential supplied here, which means there is a battery connected between this 0 volt and VBB. So this circuit and this circuit are exactly same, only thing is that the batteries are invisible in this circuit, that's it, no difference. So that is what I wanted to show you. Okay, now we want to move on to realizing those AND gates, OR gates, and NOT gate using the transistors. So let's start with that. So let me just take out that part. Here it is.